Hello everyone. In this video, you will learn the essential steps on how to design a rectangular combined footing, including the following key points: when to use the combined footing. And number two is sizing of combined footing based on loads and soil conditions. Number three is we will calculate the shear and moment diagrams for reinforcement design and shear check. And number four is the shrinkage and temperature reinforcement for the foundation and the practical tips for rebar arrangement. So let's get started with our problems. But before we proceed, let me explain quickly. As you can see here in our figure, another frequent use of combined footing occurs when one column here is very close to a property line. This is the property line, causing the usual isolated footing to extend across the line. Like for example, this one here. For this situation, the footing for the exterior column, which is this one, may be combined with the one for an interior column, as shown in this figure. So as a result, we have these types of foundation where one column, the exterior columns, is flush to the property line. So let's proceed to our problems. Design a rectangular combined footing for two columns shown in figure below, given an allowable soil-bearing pressure of 5,000 psf with a strength of steel 60 ksi, and the strength of concrete is 3,000 psi, using the normal weight concrete, and the unit weight of soil is 100 pcf. The bottom of the footing is to be 6 feet below grade, which is this one here. So basically, this is the plan of our combined footing, and this is different from the previous footing that we have uploaded, because this column is flush to the property line. So column to column distance is 12 feet, and this column here is 20 inches by 20 inches, and this column in the property line is equal to 18 inches by 18 inches. So we have the loading for dead load 120 kips, and for the live load is 100 kips for column A. So for column B, we have 200 kips dead load and 150 kips for the live load. So this is the basic sections of this foundation. So let's get started with our step-by-step solution. First, we need to calculate the total service load of the column. So for column A, we have a total load of 120 kips plus 100 live load is equal to 220 kips. That is for column A. So for column B, and that is equal to 200 kips live dead load plus 150 kips the live load, which is equal to 350 kips. So the total load for the footings, that is for column A and B, is equal to 220 plus 350 equal to 570 kips. So this is the total load of the combined footing. Now let us assume the depth of footing, which is equal to 27 inches, and the effective depth is equal to 23.5. So that is 27 minus the clear cover of the concrete plus half of the diameter of the steel bars. So the effective soil-bearing pressure at the base of the footing is equal to 5,000 minus 27 inches over 12 times 150 psf minus 45 inches over 12 times 100 pcf. This is due to concrete, and this is due to the overburdened soil. So we need to deduct the pressure due to this concrete and the soil. So the effective soil-bearing pressure is equal to 4.287 ksf. So the required area is equal to 570, which is the total load of the columns, over 4.287 KSF, that is the effective soil bearing pressure. And that would give us 132.96 square feet. So this is the required area of the combined footing. So the next one is to calculate the location of the resultant load, and this is very important because once we have determined the location of resultant load, that will be dictate the size of the footing, the length of the footing. So now, let's say we will make a column A as a reference. Let's say we'll take a moment here. So X is equal to column A times 12, and that is 12 distance from A to B, center to center, over P, the total load of the columns. That is equal to 350 times 12 over 570. So that is equal to 7.37 feet. So that is the location of the resultant load from the center line of column A. So the distance from the property line, we need to determine the distance of the resultant load from this line here, the face of the edge of the footing. So that is 0.75 plus 7.37. So the total distance from here to there is 8.12 feet. So since we have already calculated, determined the distance, we will just multiply that by 2. So by multiplying that by 2, we can determine the size in order to achieve the soil bearing pressure. So to achieve the uniform soil pressure at the base of the combined footing, the resultant load of the column must coincide with the center line of footing. So the length of the footing is equal to 2 times 8.12 feet, or equal to 16.24. So let's say we will use 16.25 feet. So now, we will determine the footing size. So the width of the footing, and that is B, is equal to 132.96 square feet over 16.25. So the width of the footing is equal to 8.182 feet, or let's say we will use 8.25 feet. So this is the size of our foundation combined footing, 16.25 feet by 8.25 feet. So the total area is 134 square feet. So that is the total area of our combined footing. Now, we will determine the factored soil bearing pressure and the factored column load. So the factored soil bearing pressure is equal to 1.2 total lead load plus 1.6 total live load, which is 250, over 134, that is the actual area of the footing, and that is equal to 5.85 KSF. So this is the factored soil bearing pressure at the base of the footing. So now the factored load of the column A is equal to 1.2 times 120 plus 1.6 times 100 live load is equal to 304. So we have here the total factored load of column A is 304 kips. So for column B is equal to 1.2 times 200 dead load plus 1.6 live load, which is 150, is equal to 480 kips. So we have here 480 kips. Now, since we have already determined the column factored column loads and the factored soil bearing pressure, we can then proceed to draw the moment diagram. So before we draw the shear and moment diagram, we will express this into a uniform load. So by converting that into a uniform load, we will multiply the factored soil bearing pressure by the weight of the footing, which is 8.25 feet. So that is equal to 48.26 kips per foot. So this is the uniform load due to the soil bearing pressure. Now, we will calculate the shear. This is our shear diagram. We will calculate the shear at point A. We have 231.6. So this shear is from 1.5 times 48.26, and that is 1.5. So that is positive uniform load going up, and that is 48.26 minus the downward load from the columns 304. So we have minus 231.6. So we have 231.6. That is the negative shear. So the shear at point 2 here, and that is equal to minus 231.6, which is this one here, minus negative shear, then plus 10.42 times 48.26. 10.42, that is from here to there. And we need to add that uniform pressure due to the soil, that is 48.26. So that is equal to 271.3. So that is the shear at point 2 here. Now we need to calculate what is the shear at point 3. So the shear at point 3 is equal to 271.3 minus, no, not minus, that is plus. From here to there, you need to add the soil bearing pressure going upward. So that is plus, positive. The sign here is very important because otherwise you will get the wrong shear. So 167 times 48.26 positive, then minus 480 kips. 480 kips, that is downward. So that is equal to 128.1 kips. That is the shear at this point here, at this point. So that is 126.1 kips. Now we need to draw, the next one is to draw the shear, the moment diagram. So the moment diagram is the shape of moment diagram is depend on the shear diagram. So here in the shear diagram, we have the linear. This one is linear. From here to there is linear. They are all linear. So this is first degree. So first degree curve, and this is the second degree curve, which is parabolic. Now the negative shear, the slope is downward. At this point where shear is 0, the slope of moment and moment diagram is 0. Then it will start to going up the slope, and because this is positive shear, the slope here is going up until it reaches to 0 slope here, which is the maximum at the 0 shear. So to calculate the moment, that is the moment from here, the maximum moment is just equal to the area of the shear. So what is the area here? Area here is just 1/2 times the width, the length from here to there, that is 4.8 plus 1.5, that is 6.3 times 231.6, this one. So that is the area of this triangle. So the area of the triangle is equal to the moment, which is 729.5 kips foot. So this is the one here. Now, the moment at this point here at 0 shear, and that is equal to the minus negative moment here plus the area of this triangle. So here, minus 729.5 plus the positive area of the triangle, positive shear. So that area is 0.5 times 6.75. 6.75 from here to there, that is 562 plus 1.13 times 271.3 kips. So the moment is equal to 186.1. So that's why we have here 186.1. Now the next one is to check the depth of the footing. Sometimes we call it beam shear. So that to check the depth of the footing according to ACI section 22.551, so the B, the maximum shear is 271.3. That is the maximum shear in the shear diagram, 273. But we need to calculate the VU sub 1, V sub U1 from the distance D. So this is the shear at the face of the column. So what is the shear at distance D, at this point here? So there are two ways to calculate this one, either by ratio and proportion. You can calculate this shear at the distance D, or just by summing up forces at this point. So the maximum shear at the distance D is equal to 271.3 minus the depth of the footing times minus 23.5 over 12 times 48.26. 48.26, that is the positive upward soil bearing pressure. And that will give us to equal to 176.8. So this is the design shear strength, shear stress, shear load for this formula. So the depth D, we will substitute all this figure here. 176,800 pounds over 0.75 times 2 times the square root of 3,000 for the concrete strength times the width of the footing, which is 8.25 feet, so multiplied by 12 to make it inches. Then that is equal to 21.74, which is less than to our assumed depth of 23.5. So our assumption of the depth of the footing is correct. It's okay. Now the next thing is to check the two-way shear or punching shear. So to check the punching shear according to section 9.611, and this is the equation, so V sub U is equal to the punching shear. So the punching shear is the width of the columns, which is 20 inches, plus the depth, because the depth here is D over 2, and D over 2 in the other side, the total is D. So 20 plus D, that is equal to 42.5 inches, which is 3.54 feet. So the B sub O, which is the perimeter of the columns, which is equal to 4 times of this width, that is the perimeter, punching perimeter, which is 3.54. So that is equal to 174 inches. That is the perimeter. Then the punching shear is equal to the load minus the punching area times the factored soil bearing pressure, which is 5.85 ksf. So that is equal to 406.7 kips. So the depth D is equal to 406,700 pounds over 0.75 times 4 times the lambda. Lambda here is 1 because we are using the normal weight concrete, and that is times the square root of 3,000 times the perimeter of the punching, which is 174. So the depth here is equal to 14.22, which is less than to our actual effective depth of 23.5. So our assumption is of the depth is correct according to this provision of the ACI code. Now the next one is to design the longitudinal steel. So that is the bottom bars. So the maximum moment based on the moment diagram is 729.5 Gibbs feet. So that is the one here. Then we have to determine the value of M. So we have here the basic equation of the flexure formula. So if we express this into steel ratio, we will come up the quadratic equation. So to solve the steel ratio, we need to find the value of M and the Rn. So M is equal to Fy over 0.85 Fc prime. So that is equal to 60,000 psi over 0.85 times 3,000. That is equal to 23.53. So using B is equal to 8.25, and that is equal to 99 inches. Depth of footing is 23.5. Then by this one, we can calculate the value of Rn. So the value of Rn is equal to mu over p BD squared, which is equal to 729.5 times 12 times 1000 over 0.75 times 99 inches width of footing. Depth of footing. That's depth width of footing times 23.5 squared, and that is equal to 213.5. So substituting all these parameters in this formula, we will have the 1 over 1765, then 1 minus the square root of 1 minus 2m Rn over Fy. So we have here 213.5 over 60,000 psi. So the actual steel ratio is equal to 0.00372. So the ES still is equal to rho BD is equal to 0.00372 times 99 times 23.5, that is equal to 8.65 square inch. I don't know what is this 0.07 by mistake maybe. So if we use the number 7 bars, that would give us a total of 15 bars. So the area is 9 square inch. So that is greater than by 9.85. Let me calculate what is the correct answer. So if we calculate this one here, 0.00372 times 99 times 23.5, so the actual, yes, 865. 865, this one should be 865 square inch. So the required bottom reinforcement, longitudinal reinforcement, is equal to 15 pieces using the number 7 bars. So now the next one is to determine the longitudinal steel bars, which is the top bars here at the under the columns. So from that moment diagram, the maximum moment is 186.1, which is this one here. So to calculate the value of M, we have the same value, 23.53. Then the B is still the same. The Rn is equal to 186.1 times 12 times 1000 over 0.75 times 99 times the depth of footing, 23.5 square, is equal to 55.5. So the still ratio is equal to, substituting all these parameters, we have 1 minus square root of 1 square root of 1 minus 2 times the m value here, 23.53, and the 55.5, that is the Rn, over 60,000 psi, and that is equal to 0.001. So obviously this is very less than to the minimum requirements. So we will check the minimum requirements per the ACI 9.612, that is 200 over Fy. So 200 over 60,000 psi, that is equal to 0.0033. So this is the governing one. We need to use the minimum reinforcement. So rho ES is equal to rho BD, 0.0033 times 99 times 23.5, and that would give us 7.35. So if we use number 7 bars, that would give us number 13, a total of 13 bars. And that is the actual is 7.8, so which is greater than the required 7.35 square inch. So the next one is to determine the transverse reinforcement. So to determine the transverse reinforcement, we need to convert the soil bearing pressure, that is equal to 480 column load over the width of the footing, that is 8.25. So we'll have, so that is equal to 58.2 kips per foot. So uniform, that is a uniform soil bearing pressure, that is the factor. So now the lever arm of the moment from the face of the columns to the outer edge of the footing, that is equal to 3.29 feet. That is came from 825 minus 1.67 feet over 2. So that is equal to 3.29 feet. So the design moment in shear direction, taking the moment at the face of the columns, is equal to 58.2 times 3.29 square over 2, that is 315 kips feet. So that is our design moment for the transverse reinforcement. So the design of the short direction, we have B, 8.22, yes, 99 equal to 99 inch. The depth of footing here is different from the depth in the previous one, because here the transverse reinforcement is in the second layer. So we have to be careful here to determine the depth. That is 27 minus 3, the clear cover, minus 1, the diameter of this bar, minus 0.5 to the centroid of this bar, to the centroid of the transverse reinforcement. And that is equal to 22.5 inch. So that is this transverse reinforcement should be placed in the second layer. And take note that the longitudinal bars should always be put at the bottom layer. So the width of the columns, assuming still spread over the width of the columns, and that is the let's say this column here, the width of the column plus twice the d over 2. So that is equal to 20 inches plus 22.5. So that is equal to 42.5 inches. So this is the effective width of the column here. So my, value of m we have 23.53, 60,000 over 0.85 times 3,000. So the Rn, the value of Rn is, we have this 315 times 12 times the 1,000 over 0.75 times 42.5 times 22.5 square, that is the depth of the footing, that is equal to 234.2. So substituting all this value here, the actual steel ratio, that is equal to 0.0041. So to check the minimum is 200 over 60,000 psi, that is equal to 0.0033, which is less than to our steel ratio, 0.0041. Now the ES rho BD is equal to 0.0041 times 42.5 times the depth, 22.5, that is equal to 3.92 square inch. So that is the required steel reinforcement in the transverse direction. And this reinforcement, let's say if we use number 7, it requires number 7, total of 7 bars. So these 7 bars should be equally distributed within the distance of 42.5, let's say from here to there. So basically, actually, practically, we need to cover this whatever if there is, just in case there is an extra concrete here. Let's say from here to there, then we will just cover that from the edge put up to the edge of the footing. So that one is number 11, number 7 bars at 7 inches on center. So the next one is the temperature and shrinkage reinforcement. So that is required based on the equation ACI 318 section 24.43. Some other footing, they just make it the same. Whatever they come after reinforcement here, they just adapt that all the way up to the other side, up to the edge of the footing here. But if you want, if you just take that effective width, 42.5, then from here to there, you can use the temperature bars. So the temperature bars, that is the calculated based on the minimum steel ratio of 0.0018 using the number 60, grade 60 rebars. So if you calculate the temperature bars in terms of spacing, and it requires 4.81 square inch. So let's say we use number 5 bars, and the area of that bar is 0.31. So the spacing is equal to 99 over 4.81 over 0.31, that is equal to 6.38. So let's say number 5 at 6 inches on center, that is top bars, short and longitudinal direction for the top bars. So that's why we have here number 5 at 6 inches top and bottom. And here also, top bars, number 5 at 6 inches on center, the same thing in the other side. So that's all, guys. That's the end of our video for the combined footings. And if you like, don't forget to like and subscribe so that you will be updated for the next upload. Thank you for watching. See you next time. Bye-bye.